Hi everyone, this is the first of several videos for 163.1.4 Combinatorics on binomial identities, and what we'll do in this video is we will prove the identities listed here. Because anything that's worth proving is worth proving twice or even 3 times, we'll give at least a couple of proofs of all of them. Okay, so before we actually prove them, let's just see what they say. So this first one says the sum from k equals 0 to n of n choose k is equal to 2 to the n. Okay, so we're keeping n fixed, and we're summing from k equals 0 up to n. So basically we're summing across a row of Pascal's triangle. Okay, so I do that for this row here. This is the 0th row. That gives me 1. Here, 1 plus 1 gives me 2. 1 plus 2 plus 1 gives me 4. 1 plus 3 plus 3 plus 1 gives me 8. 1 plus 4 is 5, plus 6 is 11, plus 4 is 15, plus 1 is 16. So 6, 16, 26, 31, 32, and so on. Okay, so if I add across a row, I get the power of 2. Okay, so that's what the first one says. So what about this next one? So here we're summing k equals 0 to n of minus 1 to the k, n choose k. Okay, and we're just doing that for n greater than 0. Okay, so as k's minus 1 to the k is going to alternate between positive and negative. Okay, so if I go across the row, I'm going to have plus 1 and then minus 1. So plus 1 minus 1 gives me 0. And for this row, we'll get plus 1 minus 2 plus 1. That's going to give me 0 again. Plus 1 minus 3 plus 3 minus 1. It also adds up to 0. And so on. So plus 1 minus 4 plus 6 minus 4 plus 1. So what have we got? We've got minus 4 gives me minus 8, and 1 plus 6 plus 1 gives me 8. So I've got plus 8 minus 8, so that gives me 0. And so on. So this is an alternating sum across the row of Pascal's triangle, and this is saying that we always get 0. Okay, so it's kind of obvious for a row like this, this is the 5th row here. We've got plus 1, minus 5, plus 10, minus 10, plus 5, minus 1. So minus 5 is going to cancel with the plus 5, the plus 10 is going to cancel with the minus 10, and the 1 is going to cancel with the minus 1. Okay, that's going to happen in this row here, because it's an odd row. Right, so the plus 1 and the minus 1 cancel, the minus 7 and the plus 7 cancel, the plus 21 and the minus 21 cancel, and the 35s cancel. Okay, so it's obvious in the odd rows, but it's not so obvious here, going across this row here. So plus 1, minus 6, plus 15, minus 20, plus 15, minus 6, plus 1. Right, because the binomial coefficients that are equal are actually coming with the same sign in this case, so it's not so obvious here. Okay, so but what that says is that so if we add up the n choose k's where k is odd, plus the n choose must equal the n choose k's when k is even, right? So all this, if I add up every second one, I must be getting the same values adding up. So here I go, the 1 plus 6 plus 1, that comes to 8, and 4 plus 4 comes to 8. So then when I do them with those alternating signs, those cancel. Okay, so if I look at 2, that actually gives me this much of this third one, right? So the coefficients with k even must give me the same sum as the ones with k odd. Okay, so this one tells me this much here, and then because these two things together add to this and are equal, they actually have to be half of this 2 to the n. So combining these two gives me that 2 to the n minus 1 right there. Okay, but we'll see we can actually arrive at this in other ways as well. Okay, so let's we've got an idea of what we're going to prove. Let's actually turn to proving them now. So for this first one, one way to do it is to use the binomial theorem. Okay, so remember that the binomial theorem says the sum, well, it says that x plus y to the n is equal to the sum k equals 0 to n of n choose k, x to the k, y to the n minus k. So what we'll just do is we'll just put x equals y equals 1, okay, and then I'll get 1 plus 1 to to the n, well that's obviously 2 to the n, and that's going to equal the sum k equals 0 to n, n choose k, 1 to the k, 1 to the n minus k, right, and so that's just k equals 0 to n, n choose k, well, exactly that, right, so we get our identity, 2 to the n is equal to the sum k equals 0 to the n of n choose k. Okay, so we can prove this using the binomial theorem, but we can also see it another way, sort of using a combinatorial approach. So let's just think about what n choose k is equal to. So n choose k, this is the number of unordered selections of k objects from n. Okay, and so that's actually equal to the number of k element subsets of an n element set. Okay, so that's you might have actually seen it even defined that way. So n choose k is the number of k element subsets of an n element set. Okay, so what are we actually doing here? This is that sum k equals 0 to n of n choose k is equal to the sum k equals 0 to n of the number of subsets of, say, the set 1 to n of size k. Okay, so that's what we're actually adding up. We're adding up these n choose k's. We're adding up the number of subsets of 1 to n of size k from k equals 0 to n, and so that's going to equal the total number of subsets. Of our set 1 up to n. Okay, and so we can use a combinatorial approach to actually figure out what that's equal to. Right, so the number of subsets of 1 to n, well, let's just think about, say, n equals 7, right? So we've got 1, 2, 3, 4, 5, 6, 7. And what we need to do to form a subset, we need to decide for each one whether to include it or exclude it. So maybe we'll go along and we'll say we'll keep that one, we'll throw out 2, we'll keep 3, we'll keep 4, we'll throw out 5, maybe we'll throw out 6 too, and we'll keep 7, right? So that gives me 1, 3, 4, and 7 as my subset. Right, and so the procedure here was we decide, so for each element of 1 to n, we decide sort of in or out. Okay, so we make a decision in or out for each element of 1 to n. All right, so we make sort of n decisions altogether between two alternatives. Okay, so and each one gives us a subset. So the ones that we choose to take in, that's going to be our subset, and the ones that we choose to take out is the ones we exclude. So so each gives us a subset. And conversely, if we have a subset, then we get a sort of a way to choose it in this way, right? So if my subset is, say, 2, 3, 5, 7, because I feel like the prime numbers, then if I want to choose 2, 3, 5, 7, then I just go no, yes, yes, no, yes, no, yes. Okay, so each subset corresponds to one of these sort of series of yes/no choices. Okay, and conversely, okay, so we end up with just by our multiplication principle, we get 2 to the n possible subsets. Okay, so we can count the number of subsets of 1 to n just using our multiplication principle. Okay, and so if we go back to our calculation before, the total number of subsets of 1 to n is equal to 2 to the n. Okay, and so just using our combinatorial reasoning, we can figure out that this must equal 2 to the n. Okay, so that's our first identity. We've given two proofs, one using the binomial theorem and the other using combinatorial counting techniques. So let's move on to the second one. Okay, so this one actually we can also do using the binomial theorem. So again, that's it, x plus y to the n is equal to k equals 0 to n of n choose k, x to the k, y to the n minus k. Okay, so what we'll do is we'll put k equal to, so x equal to minus 1 and y equal to 1. So then I have minus 1 plus 1 to the n. Okay, so that's obviously 0 to the n, and that's equal to the sum k equals 0 to n, n choose k, minus 1 to the k, and then 1 to the n minus k, which is exactly k equals 0 to n minus 1 to the k, n choose k. Okay, so we can get this just using the binomial theorem as well. But if we think about what this is saying, right? So remember, n choose k is equal to the number of subsets of size k of 1 up to n. And so what we're doing is we're adding all the ones where k is even, and we're subtracting all the ones where k is odd, right? So if I take this sum, it's k equals 0 to n of minus 1 to the k n choose k is equal to the sum k equals 0 to n with k even of n choose k minus the sum k equals 0 to n n choose k with k odd, right? So we add the ones where k is even and we subtract the ones where k is odd. So what this is actually telling us is that there's just as many subsets of even size as there are subsets of odd size. Okay. And so I guess as I said earlier, so we know that, so this is equal to, I guess from our identity, this is equal to 0, right? So that's what our identity is saying. And so so the total number of, so if I rearrange this, actually I guess I should do it on the next page, so I've got that set up for that. Right, so what we've figured out is we figured out that the sum k equals 0 to n of k even, n choose k, right? So we figured out that that's equal to the sum, so well, the sum with k even minus the sum with k odd of n choose k, that's equal to 0, and so these two things are equal. Sum k equals 0 to n k even of n choose k is equal to the sum k equals 0 to n k odd of n choose k. This thing here is actually just that same thing, just written so that we explicitly get the even ones here and the odd ones here. Okay, so there's just as many even subsets of even size as there are odd size. That's what this is telling us. Right, so the number of subsets of even size is equal to the number of subsets of odd size. And so that's going to be equal to 2 to the n minus 1, right? Because what we see from this is that half of the subsets must be even and half must be odd, right? And since so adding these two things together gives me 2 to the n, and they're each equal, there must be half of that. Okay, and so that gives us that 2 to the n minus 1. Okay, but again, so that's one way to get it through our, I guess through our sort of our binomial proofs, our binomial theorem proofs. But we can also get it a different way using the kind of reasoning we did before. We decided yes or no. So let's go back to 1, 2, 3, 4, 5, 6, 7. Okay, and say I want to choose a subset of even size of this. Okay, so maybe I say yes to 1, no to 2, yes to 3, yes to 4, no to 5, and no to 6. And then I come to 7, and I'm no longer free to actually do what I want at this point. I need to actually look back. If I'm trying to choose a subset that has even size, I need to look back and see what I've done before. And I go 1, 2, 3. Okay, so I've already I've chosen 3 things so far. If I want the subset to have odd size, then I need to include it, right? And so this choice here was forced. And if I had come through and gone yes, no, yes, 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 no, then again, I have no choice here. I have to go, I've got 1, 2, 3, 4. Okay, so I've already got an even one, and if I add this one in as well, I'll end up with something that's odd, and so I don't get any choice on that one. Okay, so this was also forced. All right, so here we were trying to get an even subset. Just in the same way, if I'm trying to choose an odd subset, then sort of my decision at the last one is forced. So if I were coming through here, so if I went yes, yes, whoops. So I went yes, no, yes, yes, no, no, and I was wanting to choose an odd subset. I've already got an odd number. If I choose this one, I'll end up with an even number, and so this decision is forced again. Okay, so the last decision is always forced. If we're trying to choose a subset that's even, or we're trying to choose one that's odd, we actually have no choice on the last one. Right, so if we want to get an even one, then we need to look back and either choose it if we've chosen an odd number so far, or leave it out if we've chosen an even number. Okay, so just using our multiplication principle, to get an even subset, we have n minus 1 choices between 2 alternatives. Okay, so in each case, we get 2 to the n minus 1 even, and also 2 to the n minus 1 odd subsets. Okay, so that's a way to derive this directly using our multiplication principle. Okay, but actually there's one more way that we can at least see that these two things are equal to each other. And I guess once we know that they're equal, we know that they must both be half of 2 to the n. And that's to use something called the bijection principle, which is another counting principle. Okay, and this says that if A and B are sets, if there's a bijection from A to B, then the size of A is equal to the size of B. Actually, this is basically the definition of two sets being the same size. Okay, so what we're going to do here, so A is going to be the even subsets of 1 to n, and B is going to be the odd subsets of 1 to n. And what we're going to do is we want to construct a bijection. So for every even subset, we want to construct an odd subset, and for every odd subset, we want to get an even subset. So if n happens to be odd, this is actually really easy. So if n is odd, what we can just do is we can just take x and we map it to its complement. So we map it to 1 to n minus x. So for example, with n equals 7, I'd say my x is equal to, say, 1, 3, 5. Then I just map it to the complement, which is going to be, what, 2, 4, 6, and 7. Right, and what you notice is this took an odd subset and turned it into an even, and it will turn an even one back into an odd one. That's because, so what we know is that so the size of x plus the size of its complement, right, is going to add up to n. And if this is odd, then this must be either even plus odd, or odd plus even. So mapping a set to its complement gives me when n is odd, it gives me a bijection between the even sets and the odd sets, and so that means there must be just as many even sets as there are odd sets. Okay, and that's actually what we saw back here in Pascal's triangle. Right, so for the odd cases, right, so this 5 cancelled with the 5. These are the subsets of size 1, and these are the subsets of size 4. And so those are the complements to these ones right here. Right? And these are the subsets of size 2. Those are the subsets of size 3. So the ones here are the complements of those ones. Okay, and so that's essentially what's going on here. But that doesn't work if n is even. So we need to do something different in general. So what we'll do here is not just for even n, it's for general n. What we're going to do is we're going to we'll single out n, right? So what we're going to do is we're going to send it to x union n if n does not belong to x, and x minus n if n does belong to x. All right, so just if I come back to say here, right? So for x is equal to 1, 3, 5. So with my n equals 7, I'm going to send that to 1, 3, 5, 7, and if x is equal to 2, 4, 6, 7, then I'll send that to 2, 4, 6, right? So here 7 is in there, so I'm just going to take it out. Right, and you can see because I'm adding one element or taking one element out, I'm going to change the size by 1. So an odd set is going to become an even set, and an even set is going to become an odd set. Right, so here we went from size 3 to size 4. Here we went from size 4 to size 3. And this is reversible because so here what my map tells me to do, 7 is not in here, so it says to put it in, and so I end up coming back to here. And in this case 7 is in it, and so I'm supposed to take it out, and that brings me back to here. Okay, so this map is an inverse to itself, and every odd set is going to get sent to an even set, and every even set is going to get sent back to that odd set it sort of came from. Okay, so this is a bijection between A and B. Okay, so because we were able to construct a bijection between A and B, they have to have the same size, and because we know that the size of A, so here we know that the size of A plus the size of B is equal to 2 to the n, and the size of A is equal to the size of B. So putting those two together, that tells us that the size of A is equal to the size of B is equal to 2 to the n minus 1. Okay, so that gives us the combinatorial way to arrive at this expression right here. Okay, so that was the first of our videos on binomial identities, and we'll be back with more.